All right, welcome everybody. Today we're going to talk about lesson number 92. This is the second day of section 12.2, so we're still talking about techniques for evaluating limits. This is kind of a nice bridge lesson because it reviews everything we've done so far, focuses a little bit more on one-sided limits, specifically in terms of piecewise functions. That's what the first set of homework problems is about. Then it also prepares you for the next lesson by reminding you of the difference quotient, which is an algebraic maneuver that we did earlier in the year, and that's what the second set of homework problems is about. Before we get to the new stuff, why don't we go ahead and do a quick reminder of what we have learned so far in chapter 12 about limits. So from a graph, you have to be able to decide, of course, does a limit exist? In order for the limit to exist, both the left hand and right hand approach have to, of course, be approaching the same value. Remember, it doesn't matter whether or not that value is actually defined. It just matters whether or not the graph is approaching it from each side. That's where the one-sided limit versus a full limit comes in. Remember, in order for the full limit to exist, you have to check both sides. Whereas if it's just a one-sided limit, then you're just either going to consider the left-handed approach or the right-handed approach. Also, make sure you know the difference between does not exist and undefined. Remember, limits do not exist, where functional values like f of 3 would be something that's undefined. From a table, you have to be able to, first of all, create a table for yourself in the graphing calculator. That would involve entering an equation into the y equals, then pulling up the table, being able to change the step values. Are you going up by a half? Are you going up by 5? Remember, you can also turn the independent variable from auto to ask, and that will allow you to plug in any value of x that you want. Once you have a table, or if I were to give you a table, you have to be able to consider both the left-handed and the right-handed approach of the y values to see whether or not the limit exists. And then you have to be able to tell me whether or not the limit is actually reached, and you'll know that whether or not whatever that value is defined or not. Algebraically, remember there are a ton of properties of limits that we went through in both of the previous videos. Essentially, you do have to memorize them, but most of them are common sense. Remember that when you're trying to find limits algebraically, direct substitution, see if you can just plug that functional value in, fingers crossed that you'll be able to calculate some number. And if you can, congratulations, that's the limit. If you are not able to calculate the limit algebraically, at least not right away, it's very possible that that's because you get something called the indeterminate form. Remember, there are many different indeterminate forms, but we have only focused so far on 0 over 0. If you wind up with 0 over 0, you're going to employ one of these 3 strategies I taught you last time by either factoring and canceling common factors. Don't forget all your factoring methods: difference of squares, difference of cubes, grouping, AC method. Rationalizing the numerator, which remember was a little bit different than rationalizing the denominator, although you're still going to multiply top and bottom by the conjugate. And last but not least, simplifying complex fractions. So for today, let's go ahead and talk a little bit more about one-sided limits. Remember that one-sided limit, you know that you are in fact only using one side if your functional value c has a superscript of either a negative sign, which means a left-handed approach, or a positive sign, which means a right-handed approach. So even though we've talked a little bit about them, let's talk a little bit more about them. So first, how would you evaluate a one-sided limit graphically? So this is now the third time maybe we've seen something like this in chapter 12. If you actually have all your stuff home from throughout the year, if you go back to the 2.6 take home that we did. I don't know if you guys remember when we were doing rational functions, you had a take home test where you were kind of investigating more difficult ones. And this was an example of one of them. Anytime you have the same factors of x or x plus 5s or x minus 6s in the top and bottom, and one of them is the absolute value, you're going to wind up with essentially what looks like a step function, 2 different pieces. In this case, each of the steps is at a value of either 2 or negative 2, because the difference between these x's is a factor of 2. If you had this graph in front of you and I was to ask you for the left-handed approach, you would be approaching 0 on this step here from the left-hand side. And I think you can easily see that the y value that you're approaching is negative 2. Notice that here at negative 2 is an open circle because you cannot actually plug 0 into this function. That will give you 0 over 0, which is, of course, indeterminate. If you were trying to find the right-handed limit, you would be approaching on this step here. And again, the y value you'd be getting closer and closer to would be positive 2. The fact that the left-hand limit and the right-hand limit do not agree means that the full limit at 0, if I were to ask you for that, also does not exist. But I also want you to be able to understand where this graph actually comes from if it was not given to you. If this graph was not given to you and I said, make me a picture, you would think about some values of x that you would plug in. Obviously, you can plug in anything other than 0. So let's say you plugged in 1. That would give you 2 over 1, which would be 2. Let's say you plugged in 2. That would give you 4 over 2, which would be 2. So any positive value that you plug in, you're always going to be reduced to a positive 2, hence this step right here. Similarly, for any negative value that you plug in, the top is always going to become positive because of the absolute value. The bottom will always stay negative, but they will still differ by a factor of 2, hence the step here at negative 2. So again, if I don't give you these graphs, you do have to understand how to produce them. And keep in mind that even if you did do this in your graphing calculator, it would be very, very hard for you to see these open circles. You would either have to know that they're there, or you would have to look at the table and it would tell you that f of 0 is undefined. As a reminder, how do you type absolute values into your graphing calculator? Remember that you type the math key, you write arrow over to the num, and then you can choose your absolute value function there. A little bit more about one-sided limits. So turns out you actually can evaluate one-sided limits algebraically. You're allowed to use direct substitution just like you would for a full limit, so long as you actually can get an answer. And then a little bit even more precise here, of course, you would hopefully recognize that this is a piecewise function. Take a look that the functional value in question here is 1, and notice that 1 is not included in either piece. So no matter what happens, I'm going to get an undefined at 1. I'm going to get an open circle. If I was to ask you to find the limit from the left-handed approach, that means that you are approaching from all the values to the left of 1, which basically means all the values that are less than 1. So that would mean that the left-handed approach would be indicated by this piece here. Approaching 1 from the left means all the values that are less than 1. Similarly, this piece here would represent the right-handed approach, because all the values that are greater than 1, that's how you would be approaching from the right side. So if you have this graph in front of you, obviously you could just look at it. If you don't, you can find the limit from the left-hand side or right-handed side by plugging in the appropriate piece. So remember, even though you technically know there's an open circle there because it's not included, because of the fact that it's a limit, you're just trying to see what value is it approaching. So here, when I ask you to do the left-handed approach, you're going to have to plug it into what would be the left-handed approach. So 4 minus 1 gives you a limit value from the left side of 3. Then when I ask you for the right-handed approach, you're going to plug 1 into the second piece. That's going to give you 4 minus 1, which is going to give you a value of 3. And then because of the fact that the left-handed approach is equal to the right-handed approach, you could actually find the full limit as x goes to 1, which would in fact be 3. So again, this is just a little different, showing that you can find one-sided limit algebraically as long as it's not, as long as there is a resulting value that's not 0 over 0. And then more specifically, here for piecewise functions, you have to make sure you're using the appropriate piece. Now, if I was to ask you to graph that previous problem, here's what it would look like. And again, I might very well ask you to do that. In fact, I definitely will. So you would have to, of course, know how this equation translates to this graph. Whether you're doing it by hand, whether you're doing it graphing calculator, you do have to understand that that's what the picture looks like. And of course, you can see right here that even though the function is undefined at 1, so f of 1 is undefined, you can find the limit from the left-hand side being 3, the limit from the right-hand side being 3, and then of course the full limit, since they're equal, would also be 3. Let's talk a little bit more about one-sided limits for piecewise functions specifically. So here we want to know whether the full limit exists. Here you have a piecewise function. Again, notice that technically 4 is not defined in either piece. Sometimes it will be, but because it's a limit, we're just trying to get very, very close. Notice that here, the left-handed approach would actually be this one because that's the values less than 4, where the right-handed approach would actually be this one because this is where the values are greater than 4. In order to determine whether the whole limit exists, you have to first start with each side. So first, let's consider the limit as x goes to 4 from the negative side. That means we're going to use this right here. So that is going to give you 8 minus 2 times 4. And that is going to give you a value of 0. Remember, even though it's not actually defined at 4, the open circle is okay because it's just a limit. You're just getting closer. How about the limit as x goes to 4, but from the positive side, which means from the right-hand side? So that is going to be the square root of 4 minus 4, which equals 0. So does the limit, full limit, as x goes to 4 for f of x exist? Well, it certainly does. Since the left-hand side equals the right-hand side, we can say that, yes, that limit does in fact equal 0. Notice in this case, I didn't have a graph. I didn't ask you for a graph. So some cases will have both. Some cases will require both. And then some cases will be, either or. Let's do one more piecewise function where you do in fact have to sketch the graph. Let's go ahead and start by finding the left-hand limit and the right-hand limit. Notice that in this case, the 2 is actually defined for the second function. So just something to be mindful of for each individual problem. The values that are less than 2, that is the left-handed approach. So that's the answer to this question. That is going to be 2 minus 1, which is going to be a value of 1. Here, the right-handed approach, that is the values that are greater than 2. So that is going to be 4 minus 8 plus 6. That's negative 4 plus 6, which is a value of 2. So the left-handed approach has a limit of 1. The right-handed approach has a limit of 2. So in part B, does the full limit exist? It does not. So no or does not exist. And then sketch the graph of f. So if I was going to ask you to sketch this piecewise function, you would, of course, sketch each piece using a couple of x values at a time. Let's start with the linear piece. So x minus 1 is true for x is less than 2. And again, technically, you can't actually plug in 2, but you can to find out where the open circle is. So if you plug 2 into that equation, you, of course, get 1, which is an open circle. Then plug in something less than 2, like 1. 1 minus 1 is 0. Plug in something like 0, you get negative 1. And here is going to be your linear piece, which, of course, x minus 1 should be. To graph the second piece, start at 2. So we know already that when we plug in 2, we're going to get a y value of 2. Plug in 3, plug in 4, plug in 5, and you're going to get piece of a quadratic. Okay, so it's very important that you not only know how to find limits from piecewise functions, but that you can actually graph them when required. Okay, so now kind of the big, most important part of this lesson is a reminder of the difference quotient. The difference quotient was actually all the way back in section 1.4. So if you need additional review, please go back there. This is the difference quotient, f of x plus h minus f of x divided by h. This was also in our calculus quick look book, even though we didn't get to really put too much in there. As a reminder, what the difference quotient is it finds the slope of the secant line. Remember, secant line means it hits the function twice. Through 2 points, we're going to call the first point x f of x, meaning you plug in some x and you get back some y f of x. And then some second point, which is h units away. So the difference from x to x plus h is h. And the difference from f of x to f of x plus h is also h. Notice that in order to actually get this difference quotient, you would have to simplify the slope formula. So here are my 2 points in question, x f of x and x plus h, f of x plus h. If you were going to find the slope, you would do y2 minus y1 over x2 minus x1. Then if you combine the bottom, that is how you wind up with this difference quotient right here. So do make sure that you write that down because we're going to use it a ton. Why are we going to use it a ton? Well, we're going to be asked to find some limits that directly relate to calculus using the difference quotient. So in order to use the difference quotient, I can just say, use the difference quotient and then give you an f of x, or I can actually ask you to do it for a specific x value. So here, I'm telling you that the function is x squared minus 1, and I'm asking you to find the limit as h goes to 0 of 3 plus h minus f of 3 over h. So this is a specific application of the difference quotient where x is equal to 3. Again, sometimes I will do that, and then oftentimes I will just leave it as an x. Just like always, when you're asked to find a limit, you should go ahead and try to just plug it in. When they ask you for f of 3 plus h, that means go to the f function. Everywhere there's an x, put a x plus h, or in this case, 3 plus h. So that's how you get 3 plus h squared, and then don't forget the negative 1. Then you're going to subtract whatever f of 3 is. What does f of 3 mean? It means go to the f function. Everywhere there's an x, put a 3, and then don't forget the minus 1. Do the FOIL, distribute the minus, combine like terms. Lots of things should cancel. The 9s will cancel. The 1s will cancel. Notice that you're only left with values that have h's in the numerator, and spoiler alert, that should always be the case. Unfortunately, if you try to plug in 0 over 0 to 6h plus h squared over h, you're going to get that nasty looking indeterminate form. But the good news is, because of the fact that everybody has an h, you're going to use our factoring and canceling strategy by factoring out an h, reducing an h, and then finally plugging 0 into 6 plus h gives you a final answer of 6. So kind of the moral of this story is that anytime you're asked to apply the difference quotient to a limit, you are always going to get 0 over 0 unless you do some simplification. So lots of things should reduce, lots of things should cancel, and you're going to do that by using the strategies that we went over in the previous video. So a couple more examples here. The function in question is 2x squared plus 1, and I am again asking you for a specific application of the difference quotient, which in this case is at 2 plus h. So in order to do this, I'm going to start off with the limit as h goes to 0 of, in order to find f of 2 plus h, that means go to the f function. Everywhere there's an x, put a 2 plus h. So 2 times 2 plus h squared plus 1, that's f of 2 plus h, minus f of 2 means you're going to, everywhere there's an x, you're going to put a 2, and then don't forget the h in the denominator. To save a little space, I'm going to drop the limit statement for now, and I'm going to do the numerator. So in the numerator, you're going to go ahead and do the FOIL. So 2 plus h squared is 4 plus 4h plus h squared plus 1. 2 times 2 squared is 8 plus 1. So that is going to be, minus 9, or minus 8 minus 1. Okay, so then, and it doesn't matter if you calculate first and then distribute, or if you distribute like this. Again, saving a little bit of space, if you distribute now this 2, that is going to give you 8 plus 8h plus 2h squared plus 1 minus 8 minus 1. This is where the beautiful, glorious things should start happening. The 8s, a cancel. The 1s, a cancel. What you're left with in the numerator is 8h plus 2h squared, and then don't forget that original h from the denominator. Again, I get a little bit lazy sometimes, and I drop it throughout, but don't forget to put it back in at the end. Once you realize that everybody can reduce by h, we're ready for almost the final step. So put your limit statement back in. You are finding the limit as h goes to 0, reduce an h, and an h. That is going to give you 8 plus 2h. And then if you actually go ahead and plug a 0 in for h, you're going to get a final answer to this question, which has a limit of 8. So again, this is a specific application of the difference quotient because of the 2, but we're going to do plenty that are just the general application. So for this radical function, you're now going to find the limit of the difference quotient. So everywhere there is an x in the function, you are going to start by plugging in x plus h. So f of x plus h in this case becomes the square root of x plus h minus 2. Can't really be simplified, looks a little bit nasty, but that's what it is. Minus the f of x is just the square root of x minus 2. And then, of course, don't forget the h in the denominator. Okay, well, what do you do from here? You know, if you try to plug in 0, you're going to get 0 over 0. That's not going to work. Hopefully you remember, oh man, all those radicals, I need to go ahead and rationalize the numerator. So start by adding parentheses on the top. The conjugate of the numerator is the same front, x plus h minus 2 square rooted. Change it to the opposite sign, which is addition, all over the same back. And of course, you have to do it in the numerator and the denominator. Drop my limit statement for now. In the numerator, when you multiply the square root of something times itself, you're going to get whatever is under the square root, x plus h minus 2. Then when you do the last, remember technically it's a FOIL, but you only need first and last. A negative times a positive is a negative, and then it's negative the entire quantity x minus 2. So please don't forget to distribute that minus. This is, of course, all still over h times the square root of x plus h minus 2 plus the square root of x minus 2. And hopefully you remember that my advice is do not multiply out the denominator. The whole point of this is that things should cancel. So speaking of things canceling, let's make sure we do it in an organized fashion. In the numerator, x plus h minus 2, distribute the minus. That is going to be equal now to h over this entire thing. As you go to reduce, do it carefully. So x minus x cancels. Negative 2 plus 2 cancels. This h over this h cancels. And now we're almost ready for the final step. So everything in the numerator canceled, which means there's technically a 1 there. And then don't forget to put your limit statement back in. So the final calculation I'm going to do is the limit as h goes to 0. All that's left in the top is 1. And then the bottom, square root of x plus h minus 2 plus the square root of x minus 2. If you now plug 0 in for this h, you're going to get 1 over the square root of x minus 2 plus the square root of x minus 2. If you have 2 square root of x minus 2s, so that's 1 on the top. And then if you have a square root plus a square root that are the same, you're going to get 2 square root of x minus 2. And it turns out that is in fact the answer. You could technically rationalize the denominator if you want to, but actually for the purposes of this lesson, you don't actually want to. So hopefully you're kind of seeing that there are patterns. Lots of things should cancel. And again, you're using those strategies that I taught you last time. One final problem for the day. Again, you're trying to find the difference quotient, and now we've got some fraction action. So this is the limit as h goes to 0. F of x plus h means everywhere there is an x, you're going to put an x plus h. Then you're going to straight up minus whatever f of x is, and this is all, of course, over h. Now, how do you get rid of all these crazy fractions? Common denominator. So put each of these in a parentheses. The common denominator of x plus h minus 1 and x minus 1 is just those two things times each other. Looks a little strange, but that is in fact the case. If you multiply this x plus h minus 1 times x minus 1, that means this becomes x minus 1. Big fat minus here, don't forget. In order to take this x minus 1 and turn it into a common denominator, you're going to have to multiply this times x plus h minus 1, and you're going to have to make sure that you distribute that minus. Remember, this is technically h over 1. How do you get rid of the complex fraction? Well, here's the keep. Change it to multiplication and then flip it to 1 over h. All right, a little bit of simplifying. So this becomes x minus 1 minus x minus h plus 1 all over x plus h minus 1 times x minus 1 times 1 over h. Cancellation nation, but carefully. So x minus x, -1 plus 1, and then you have a negative h on top and a positive h on the bottom, you can reduce those, but of course it reduces to be a -1. So in our final calculation here, we're finding the limit as h goes to 0 of -1, which again comes from reducing negative h over h, over x plus h minus 1 times x minus 1. If you put a 0 in for h, you wind up with -1 in the numerator. You wind up with x minus 1 times x minus 1, which of course we're going to write as x minus 1 squared.